This is part 1 of chapter 8 in Timberlake, and we're going to be covering acids and bases. The topics for this part are Arrhenius acids and bases and their properties, acid strength, and Bronsted-Lowry acids and bases, and then Kw, constant for water. So let's start off with Arrhenius acids, and we have some examples over here. We have some vitamin C, we have an orange, we have a can of cola, and some vinegar. All these solutions are acidic. So Arrhenius was the first person to come up with a definition for acids based on chemistry. Before this, people thought that acids contain little bits of broken glass and tiny nails, because if you get an acid on a cut, it stings like anything. But this is the first molecular definition. So acids produce hydrogen ions in water. So you need water to have acids, according to Arrhenius. And here's a little equation showing that. So HCl gas, which is hydrogen chloride gas, reacts with water to produce hydrogen ions and chloride ions. Now, acids are electrolytes because they produce ions. They have a sour taste. They turn litmus red. Litmus is a dye, and many dyes change color if you go from an acid to a base, or even if an acid gets weaker. And people used to use these dyes to know when they had an acid or a base. So litmus is a very common dye. Acids also neutralize bases. And this is what happens in water. A hydrogen ion, which no one thinks really exists by themselves, will easily combine with the water molecule. It's actually attaching itself to the oxygen atom of the water and produce what we call a hydronium ion. So when we talk about acids, we usually talk about hydronium ion concentration, but we can write H plus as a shorthand way of writing H3O positive. So you want to remember that as we go through the video. Here are some names of common acids. Let's go through some of these now. We have hydrochloric and hydrobromic acid. These are called binary acids because there are only two elements in the formula. Whereas these other compounds, these are all acids and they're called ternary acids because they all have three elements. Now you notice that the shorter formulas have the longer names. So these binary acids begin with hydro and they end with IC. And the middle of the word tells you about that other non-metal. So use chlor for chlorine. And in water you get this anion, chloride. Now there's a link between the IDE then and the name of the acid. So you notice with hydrobromic acid we would get a bromide. Now if you look down at some of these ternary acids, we have nitric and nitrous. You've seen these endings previously. And so nitric means more oxygen and nitrous means one less. And from nitric acid you get nitrates, and from nitrous acid you get nitrites. So the ATE of nitrate goes with the IC of the acid. ITE goes with OUS. So there is a system to this. Then we have, you notice, sulfuric and sulfurous, sulfate, sulfite. And we have carbonic acid. That's the acid in carbonated beverages. Phosphoric acid is in Coca-Cola. You have chloric and chlorous acids. And then down here at the bottom, we have one of the earliest acids ever known called acetic acid, the acid that's in vinegar. And that's named after the Latin word for sour, which is acetum. And here's another table where we have some common strong and weak acids. You notice that there aren't that many strong acids. And there's a whole bunch of different weak acids. What really makes an acid strong or weak is how much it ionizes in water. So if you have hydrochloric acid, this is how we picture hydrochloric acid to be. Within the acid, we have just ions everywhere. There are no HCl molecules at all. It's just either hydronium ions or chloride. Now with the acetic acid, you notice we have a lot of molecules of acetic acid that never reacted with the water. So we have very few ions. So that's what it means to be ionized. It really means how many of the molecules have actually changed to ions. So not many in a weak acid. And this diagram is going to show you the same thing. For a strong acid, if we initially have HA molecules, when the reaction is ionized, there is none left, and it's all in the form of ions. Whereas for the weak acid, our initial weak acid HA, and at the end, still mostly HA, very few ions produced. Now let's go over Arrhenius bases. So an Arrhenius base is a substance that produces hydroxide ions in water. And you can see over here the sodium hydroxide in water producing sodium hydroxide ions. It produces a lot of them. And this process is called dissociation because the ions are already present in the solid and the water is able to break them apart or dissociate them. Arrhenius bases, in fact, all bases taste bitter or chalky. And they're electrolytes because they produce ions and they feel soapy or slippery in your hands. That means that soaps and detergents are bases. And they neutralize acids. So acids and bases neutralize each other. And here are some common bases. These all have hydroxides in the formula so you can recognize them. You see the OH. Now you can't tell by looking at these formulas if they're strong or weak. You might think that the strongest one should be the iron 3 hydroxide and the aluminum hydroxide because there are 3 OHs in the formula here, only one up here. And you'd be exactly wrong. These two are the strongest and these guys are the weakest. And here are some bases that you would have at home. Now we have Easy Off oven cleaner, baking soda, Windex, we have detergent, and we have Drano. Drano is a very strong base, and I would imagine that the oven cleaner is a very strong base as well. Baking soda itself is a weak base, and you put that in refrigerators to absorb these acidic odors that we get from foods. And we have Windex, which contain a weak base, and Cheer also, a detergent, would be a weak base. Now, the Bronsted-Lowry theory of acids and bases is a little bit different and a little bit more general. An acid donates protons to bases, and a base accepts protons from acids. I'm going to get my pen down here. Now, okay, so acids are proton donors and bases are proton acceptors. Well, let's see, here's an example here where we have HCl and water. Now, if you look on the right-hand side, you notice how the HCl is becoming Cl. That's supposed to be Cl minus, and left out the charge there. And the water is becoming hydronium ions. So what's going on is that the HCl then is giving up an H positive. Let me go back on that too fast. So there's an H positive coming from this. See if we think of that as being positive. This guy is going down to the water, becoming H3O, and the water is accepting that H positive. So the HCl is the acid and the water is the base. Now down here we have a different situation. Now we have NH3 becoming NH4 positive. So the NH3 is accepting that H positive ion, and the water on the other hand is becoming hydroxide. It's releasing that hydrogen ion. So by definition then, the ammonia, because it's accepting a proton, is the base, and the water is an acid. So here we see water can be an acid or a base under this theory, which is not the same case with the Arrhenius acid and base theory. Now how acids and bases neutralize each other, we're going to see right now. So let's say we take HCl, hydrochloric acid, and potassium hydroxide, and we put them together, and we get water and potassium chloride. The actual chemical reaction is the H positive from the acid combining with the OH from the base, producing water. And that's how they neutralize each other. Now what if you have a different type of base, one that's not a hydroxide, like here? Here we have sodium carbonate. Now sodium carbonate is in baking powder, and you can also find it in many antacids. Now in sodium carbonate, you don't see any hydroxide here. So how is it able to react with the acid and neutralize it? Well, let's take a closer look. From the acid, we get hydrogen ions. We get two of those. You notice the two in front. From the sodium carbonate, we get the carbonate ions. Now these guys can combine together to form H2CO3. We are here, H2CO3, which is actually a very weak acid. And this thing breaks up quickly into water and CO2. So that's why at the end of the reaction, we just have water and carbon dioxide. We have a neutral solution. So acids and bases that neutralize each other mostly by becoming water. Okay. Now in distilled water, which is water that's and purified, there's nothing in it, we figure that some of the water can break down into hydrogen and hydroxide ions. But for every water molecule that does this, you'll get one H positive and one OH. So you never get more than one of each. Now in distilled water, these are the molarities of them. 10 to the negative 7th moles per liter, which is really small. It's 1 times 10 to the negative, that's actually 10 to the negative 7th would be 1/10 millionth of a mole per liter. That's really, really small. Now we're going to use brackets around formulas to mean molarities, so we don't have to write that in anymore. So in a water solution then, if you were to multiply these two numbers together, you'd wind up getting this number, which is called Kw. It's also called the ion product of water. So when we multiply powers of 10, we just add the powers together. So you'd have negative 7, plus negative 7 equals negative 14. And that's how we get that. We're going to use this equation here when we have one of these and we're looking for the other. So let's check out in acids and bases and see what about these concentrations. So we have an acidic solution. In the acidic solution, we have a greater concentration of hydronium ions than hydroxide. So you notice a larger amount of hydronium here. In a neutral solution, these concentrations are equal. And in a base, the hydroxide wins out. But one thing to notice is that no matter whether it's an acid or whether it's a base, you always have both of these ions present. It's just which one is present in a greater amount. Now let's take a look at this chart. Here we have a Kw value, which is going to be the same. And remember, when we multiply H positive times OH negative, we're always going to get that Kw. So you can see how it works out here. These concentrations are equal. We have a neutral solution. Now, you notice if you're multiplying these two together, you're really taking the negative 2 and adding the negative 12 together. And that's how we get the negative 14. So if you were looking for one of these and you knew the other, it'd be pretty easy to get it. Like if we skip down here. Let's say you didn't know that this was 10 to the negative 8th, but you knew this one. You knew this was 10 to the negative 6th. Then you could just say, what do I need to give me negative 14? That works as long as the numbers out in front here are ones. But you notice like in the middle, if there's something different, it doesn't quite work out that way. And down here, the same thing. So which make these things acids or bases? So remember, whichever one of these guys is greater tells you have an acid or a base. So the acidic solution here, it tells you that this number, 1 times 10 to the negative 2nd, is greater than 1 times 10 to the negative 12th, which is true. So you must remember that 10 to the negative, like down here, 10 to the negative 6th is a bigger number than 10 to the negative 8th, and that's why this is basic, because the hydroxide concentration is greater. So let's take a look at a sample question now. What is the hydronium concentration of a solution if the hydroxide is 5.0 times 10 to the negative 8th? Right, so what we're going to do first is write the constant for water. Kw equals hydronium times hydroxide, and that's our value. Then we're going to solve the expression for the hydronium concentration. So if we just look at this here, let's say I forgot about this guy for now. If I look at what I have here, if I want to solve this for hydronium, that means I'd have to divide both sides by hydroxide. And the hydroxide would cancel out over here, and that's what we're left with. And then I would just go and I would plug in my 5.0 times 10 to the negative 8th, and I would solve for that, and I get 2.0 times 10 to the negative 7th. Now one note about putting these numbers into your calculator. Remember that we're going to be using the EE button or exponent button on the calculator. So if I want to put in 1.0 times 10 to the negative 14, I'd put in 1, I wouldn't bother with a 0.0, and then it's going to be EE. A lot of you have that button, EE. Not too easy to write with this. Sometimes it'll say EXP instead. And then I'd have to hit my negative positive sign. So for positive slash negative, sometimes it might just show you a negative sign. It might look like this, just a negative in there. And then I'd put in the 14. What you don't want to do is put in 1 and then the times and then try to put this in, because it's going to throw you off completely. So that's what I would do to get this number in, and then I repeat it. And for this one, I would say then divided by, 5 EE, and then I want -8, so it's going to be my negative, positive negative button, and then I'd put in 8, and then I put equals, and then I will get that for an answer. Now, it might not look like this when you do actually do it on your calculator, but you get kind of used to it. All right, why don't you guys try this one on your own? So pause the video, try this one, then come on back and see what the solution looks like. Okay, and here's the solution. So write down our formula. We have Kw equals hydronium times hydroxide is our value, and I'm looking for the hydroxide. So I'm going to have to divide both sides by the hydronium. That way the hydronium will cancel out over here, and this is what I'm left with. And so I'm going to put in my hydronium value. And just as I showed you a moment ago, it'll be this divided by that. Now let's say you want to estimate, so you don't get it wrong. If you ignore the 2 and act like that's a 1, that would really be then 10 to the negative 14th over 10 to the negative 3rd, which means 10 to the negative 14. Remember, and then you're subtracting that negative 3rd, which is really 10 to the negative 14 plus 3, which would give you 10 to the negative 11th. So are you going to get 10 to the negative 11th? No, because of the number 2 here. If this had been a 1, that's what your answer would be. So you should expect then to get a number that'll be like something times 10 to the negative 12th, a little bit smaller than this. And we get exactly that, 5 times 10 to the negative 12th. Okay, next one. All right, why don't you try this one and see how you can do. So here you're looking for the hydronium concentration, and they give you the hydroxide of ammonia. That's what we have there. Okay, so we're going to write Kw for water. Remember, pause the video and see if you can finish it. All right, here's the rest of it now. And then I'm going to solve for my unknown. So remember, to solve for my H3O, I'm going to divide by the OH now on both sides. That's an U. And that'll cancel out here. And I get that. I'm going to plug in my number, and I get my answer. So sometimes we have to do this kind of thing. Not too often, but it's handy to be able to do it. And that's the end of the slideshow.